So without further ado, let me introduce you to our next speaker, Professor Yang Yue from National University of Singapore. Professor Yang he did his BSc in mathematics in Peking University, and then he did his PhD at Cornell University under Richard Shor in recursion theory, I believe. And
Yes.
okay, so I know Professor Yang from many years ago in Singapore when attending the summer school, and he has been a good friend and a teacher to me. So without further ado, I will pass it on to Professor Yang.
Can I share my screen?
Oh yes, let me make you the co-host. Okay, where are you? Okay. Okay, you should be able to share a screen now.
Are you able to see the screen?
Yes. Yes.
Okay. So, okay. Can I start or?
Yes, go ahead.
Okay. So first, I'd like to thank Zhu Yao for inviting me to give a lecture in the inaugural conference of the Logic Association of Malaysia. So Singapore is very close to Malaysia, and I hope we'll have lots of fruitful communications in future. Okay, so today I'm going to give a survey talk on some of the works which I have been doing. So it's about reverse mathematics, especially related to Ramsey theorem. So, so the talk was based on the joint works with many people. Professor Chong and Dr. Li Wei are my colleagues in National University of Singapore, and Liu Lu and Wang Wei are some Chinese colleagues in China. Okay, so I'm going to speak on two parts. So the first part is some background. Unfortunately, I cannot avoid lots of technical terminologies, so please bear with me. And then I'll report some of the recent works which we have done on the Ramsey theorem for trees. Okay, so I'll start with reverse mathematics, which is okay. It's not a separate branch in mathematical logic. So it's a branch in mathematical logic. Somehow involve all four main theories in logic, like set theory, recursion theory, model theory, and proof theory. So to give a simple description, so the goal of reverse mathematics is to find out the exact axioms that are needed to prove some mathematical theorems. So why we want to do this is because in order to find out the exact axioms, we need to discover new proofs, because based on the strengths of the axioms, you could have different proofs. If you have a stronger axioms, you could have a very short proof. But suppose you have a weaker theorem, somehow you need some more tedious or more clever, depending on how you look at it. So you must have some different new proofs. Okay, so in my talk, I'll focus on combinatorial principles such as Ramsey theorem, pigeonhole principle, or weak Koenig lemma, etc. So now in my study, the relative strength is measured by first order and second order arithmetic. So let me briefly say something about the first order and second order arithmetic. So essentially, we are going to to use these to measure the strength of mathematical theorems. So you don't need to remember all these names, but roughly you remember it is of strength 1, strength 2, strength 3. So as long as you have a relative sense of the strengths, the exact name doesn't matter. Okay, so for the first order strengths, we are going to use induction schemes. So here, the I sigma n stands for the mathematical induction scheme for sigma n formulas. So induction is the usual thing we learn in elementary in high school. So it says if a statement for a statement phi 0 holds, and from phi n you can get phi n plus 1. Then for all natural number phi holds, for all natural number n, phi n holds. So that's the usual induction scheme. Now sigma n formula means you only have n quantifiers, alternating blocks of quantifiers, and begin with a existential. So I sigma n stands for the sigma n. The induction scheme holds only for sigma n formulas. So roughly, in my talk, I will involve. So I'll treat this as a base level. Sorry, the writing was not. And then this part is maybe the second level, and then this probably is a third level. I will not use higher level, but some other people in reverse mathematics may use higher levels. Okay, so that's the first order part. For the second part, for the second order part, reverse mathematicians use something called the Big Five. So I don't have time to explain the names, but basically here is the basic level, the base level. And this is level 2. This is the second level, and this is the third level. Okay, so WKL0 is for the weak Koenig lemma, and this is for the arithmetical comprehension. So as I said, the exact statement doesn't matter. Okay, but the relative strength probably is all I need in the talk. Okay, so now we look at this famous theorem in combinatorics. So let me remind you the Ramsey theorem. So we use this bracket, square bracket A to the power n to denote the set of all n elements subset of A. So usually, okay, for recursion series, all sets are subsets of natural numbers. Okay, so the Ramsey theorem says, suppose you have, we call it a coloring. Suppose you have a function f from the n element subset of natural numbers to k. So this is this represents the possible k coloring, right? So you can color the n tuple or n element set by color 0 or color 1, or color k minus 1. So if you have a coloring like this, then Ramsey theorem says there is an infinite so-called homogeneous set. So there's an infinite set H such that if you restrict F to the n element subset taken from H, then you only have one color. Okay, so there are lots of sort of philosophical interpretation of these. They're saying absolute chaos is not possible, or so no matter how hard you try to make make a coloring random, there's always some order, which is the homogeneous set. Also, there are lots of interpretations, lots of fun interpretations like that. But we are interested in the first order and second order strengths of these. Okay, so people in reverse mathematics usually refer to statement like this as a problem, as solutions against the problems, right? So the statement says for all f, there is an h. So we would think that somebody posed a problem to us. So F will be the problem, the H will be loosely called a solution. So that I will not say this long statement, I just say there's a solution. So you give me a coloring problem, there's a solution. Okay. So there are two parameters there. One is n, the other one is k. So the version above is denoted by RTNK, this Ramsey theorem version NK. And RT1 is a shorthand for OK RT1K holes. So this is the usual pigeonhole principle. So you have 5 pigeons, 4 pigeonholes, then then some pigeon must share the same pigeonhole. That's the pigeonhole principle says. Okay, so in the study of reverse mathematics, it is Jakosh who did the first work. I state his theorem in terms of reverse mathematics. So originally he used a different language. He used a recursive mathematics language, but I transfer them into the language of reverse mathematics. So Jakosh says, for any natural number n and k, the RT32 or any RTNK for I forgot to say n and k is bigger than equal to 3. For any larger nk, the strength of Ramsey theorem is at the third level. So this is the third level. Okay. So if the n element set is more than 3, or you color it more than 2, then the strength is known, is at third level. But however, he is unable to decide what about the younger brother, the smallest guy. So you color the pairs by 2 colors. So he can derive that it is not beyond third level. So certainly this is simpler than others. So he is not, AC0 certainly can prove this RT22. And the second level is not enough to prove him. But the exact level we don't know. So this is the second level. So he knows that, so ACA0, this is a place where all the RT and K, and so the RT22 is definitely below or equal to it. But the next level, the second level, cannot prove this Ramsey theorem for pairs. And for the first order strength, again, this RT22 can imply the second level. But it is, at this moment, it is not known. At the moment of Hurst result, it is not known whether RT22 can imply I sigma 2, the third level. Okay. So by the way, the pigeonhole principle also implied B sigma 2, the second level. So from Jako's result, we know that among the family of Ramsey theorems, this Ramsey theorem for pairs, although it is the easiest one, but somehow it is the special one because we are unable to locate the exact strength of RT22. So the next breakthrough is in 1995 by Siderpen and Slayman. So they confirmed that this the RT22, the younger brother, is really younger than the rest of the family. So the RT22 is this guy is definitely below the third level. So this is the third level. So RT22 is strictly below it, right? And we know the second level cannot prove it. Okay. So their proof make clever use of trees. So Siderpen made this conjecture that the RT22 actually imply the second level. So RT22 is sort of between the second and the third level. So that was Siderpen's conjecture. So, and then people really tried to pin down the exact strength of the RT22. So in the from 1995 to recently, then lots of works has been done. They get closer and closer. So I'm going to list some of the partial result. So in 2001, Cholak, Jackosh, and Slayman showed a few results. So the first result is they have a decomposition. So they decompose the Ramsey theorem for pairs into two versions. I don't have time to explain the meaning. So it just split into two other principles. And then this splitting was extremely useful because you can use this decomposition to do the divide and conquer. And a lot of theorems are proven through the divide and conquer. And also they show that every RT22 has a low 2 solution. Again, I'm sorry, I don't have time to explain what low 2 is. And they show that RT22, for the first order strengths, the RT22 cannot reach level 4. So this is level 4 of first order. So remember, we know that RT22 is stronger than level 2. Now they know by the CJS, they know it is definitely weaker than level 4. Okay, and this is a very influential paper, and so it generates lots of heat to the problem. Okay, and then a few years later, Hershey and Shore had a paper called Combinatorial Principles Weaker than the Ramsey Theorem for Pairs, because it's very hard to tackle the Ramsey Theorem for pairs directly. So people try to follow the divide and conquer method, try to look at simpler combinatorial principles, and try to find some clue to attack the Ramsey Theorem for pairs. So this is some of the combinatorial principles weaker than Ramsey theorems showed mentioned in their paper. So in particular, the decomposition of C-dependent, CJS, Cholak, Jackosh, and Slayman, the code was really weaker than RT22. So it is open whether SRT22 is strictly weaker than RT22. So so the impact of RT22 it caused so-called paradigm change in a reverse mass. So if people are familiar with the history of reverse mathematics, for example, in the main reference book written by Simpson, there you have the big five: RCA 0, WKL 0, ACA 0, and the other two. So they are big five. They are linearly ordered. So in the first 30 years of reverse mathematics, people try to put every mathematical theorems into one of these levels. So they have done a lot. So the whole book of Simpson, there are hundreds of theorems which are classified to be equivalent to these. So the big five looks very, very nice, right? So there's only 5 of them and linearly ordered by strengths. So you can classify mathematical theorems in a very neat way. But because of the Ramsey theorem, the picture becomes something like this. So it's very chaotic and lots of things floating around. So so it depends on your interest. Some people are like this chaotic thing, right? So it looks more exciting, but some people like order. So some people would prefer this picture. So the impact of Ramsey theorem somehow change people's idea about reverse mathematics, right? From this very neatly well-ordered system into this this zoo. We call it zoo. Actually, the picture I download was already too old. So you can go to some website, and there are more animals in the zoo now. Okay, so let me continue. So more recent results. So in the year 2011 or 2012, Liu Lu, a Chinese logician, finally solved the question about sediment conjecture. So he confirmed that the picture is like this. So this is level 1 for the second order strength. And WKL is a level 2, ACA0 is a level 3. So he confirmed that this RT22 is to the side. Okay, so we know that this is stronger than this is stronger than this. And Liu Lu's result confirmed that from WKL0 you cannot get RT22, and also from RT22 you cannot get WKL0. So indeed, this definitely break this nicely well-ordered 5 points. Right? And Ramsey theorem is one of the major theorem in combinatorics. So this is a very natural example of a mathematical theorem which doesn't fit into the big 5. Okay. And with Chitad and Ted Slayman, we showed that the stable version of Ramsey theorem does not imply Ramsey theorem for pairs also. And also the stable Ramsey theorem for pairs does not prove I sigma 2. So it's weaker than the level 3. So we use a non-standard model of arithmetic to achieve this goal. And later we improve the result by showing, we show that the Ramsey theorem for pairs does not imply I sigma 2. So on the first order strength, the Ramsey theorem for pairs also in between. So I sigma 2 is level 3. So this is level 3. And this is level 2. B sigma 2, sorry. B sigma 2 is level 2. Just now, Hurst, I show you the Hurst result says RT22 implies B sigma 2. And we show that this RT22 does not imply I sigma 2. So the first order strength is between B sigma 2 and I sigma 2. Okay. And more recent result. So in 2018, Pate and Yokoyama showed the Ramsey theorem for pairs is pi03 conservative over RCA0. Actually, this also have some philosophical implication. So in the long introduction of their paper, they mentioned quite a number of consequences of their result. So unfortunately, I don't have time to get into it. More recent result is by Monin and Partey. So they showed that stable Ramsey theorem for pairs does not imply RT22 even in the standard models. So with Chita and Slayman, we showed using non-standard models, but actually over standard models, the non-implication still holds. So this is the technically, I mean, it's a completely different techniques. Okay, so until now, I guess most of the major open problems around RT22 are solved with these results I just mentioned. So I can mention one open problem. So the open problem is whether the Ramsey theorem for pairs is pi11 conservative over RCA0 plus B sigma 2. So they show that it's pi03 conservative or RCA0, but it is not known whether this is a pi11 conservative. So this is one of the main open problems still remains in this field. Okay, so that's the first part of my talk, which is the sort of the survey of the background. So now I want to move on to some of the ongoing project. Okay, so now most of as I said before, most of the problems around Ramsey serum pairs are solved, right? So what's next? So people have tried. So people say maybe we can have a stronger notion. I mean, to characterize the theorems, we can choose some other other measures. They use Weyrach reducibility and something else. So I don't have time to do this. And recently, I heard a talk by Ludwig Partey. So they can generalize Ramsey theorems. They call it like Ramsey-like theorems. So sometimes, if you want to find the homogeneous solution, it's hard. It tends to be hard. But if you relax a bit, say, I don't need a homogeneous solution. I don't need to have one color. Maybe you can give me just two colors. So I relax my standard. So I don't want purely homogeneous set. I allow the color, but with a bound. Say I allow two colors or three colors. So those things, sometimes the theorem become much easier to prove. So they studied those Ramsey-like theorems. And of course, you can look for other zoos. So the zoo around Ramsey theorem is just one of the combinatorial theorems. Maybe around some other combinatorial theorem, there's also very strange animals. So, for example, Hindman theorem or dual Ramsey and etc. Right now, in my talk, I'm going to talk along the following lines. So I'm trying to look at Ramsey type result on structures. So this is influenced by set theorists and combinatorials. For example, Stevo Todorchevich and other people. So we can study the structural Ramsey theory. Okay. So the typical problem is this. So Ramsey theorem, remember, is coloring some n-element subset of natural numbers. Now, what happened if we add some structure over these sets, right? So if the set that we color has a structure on it, can you always find a homogeneous substructure, right? Which is isomorphic to the original one. In 2009, Schub, Hurst, and McNichol, they studied Ramsey theorem for trees in reverse mathematics. And recently, many people studied a similar theorem like Devlin's theorem on rational numbers, Rado graphs, and Millikan's tree theorems. So they all belong to the banner of structural Ramsey theorem. So let me focus on Ramsey theorem for trees, right? So suppose we have a full binary tree like this, okay, of height omega. So suppose we color every pair of nodes with k colors. So give me a pair of nodes, say give me sigma, give me a tau. Right? So I color sigma tau, say color this, color 0 or something. You give me another pair, sigma prime, tau prime, I color it 1, right? Sigma prime, tau prime, I can color it 1. So you color every pair of nodes with k colors. So the question is, can you find a homogeneous subtree which is isomorphic to the original tree? So it's still a perfect tree and always branching. Now we need to add, so the example I give you, the example here doesn't work. Definitely, this is a bad example because we have to add some reasonable restrictions to avoid some trivial examples. For example, if I color all the comparable ones using one color, all the incomparable ones using another color, so any homogeneous set has no chance to be a tree. I mean, either they are all on the line or they are all, it's like either they are, the homogeneous set is a chain or is an anti-chain. So there's no chance to be a tree. So we have to add some reasonable restriction so that the problem is more interesting. So what they did is they only color the comparable pairs, right? So the notation is, so this is the tree, this is the perfect tree. So you color the pair of nodes, but you add a restriction. So the pair of nodes are comparable. Okay, so you only consider comparable nodes, and then you have this the Ramsey theorem for trees. So you have TT NK. So it's similar to RT NK. So N and K are natural numbers. So the theorem says for any coloring of the N element subset of nodes, which are all comparable to K colors, then there is a homogeneous tree which is isomorphic to the original full binary tree, right? So this is what I mean by, suppose we color a structure, right? It's like a tree. We color a tree, and then we want to find a solution, which again is a tree. It inherits the same structure, and it gives you the how to say, they are homogeneous. They give you a solution which is isomorphic to the original tree. Yes.
The subset T is a proper subset, right?
Yeah, so they're depending on the color, right? Suppose you color everybody the same color, then you can take the full tree. Sorry, yeah. So, but that's I mean, our opponents usually are very bad, right? So they try to make our life more difficult. Okay. So I hope I'm more or less clear about the Ramsey theorem for trees. So now I'm going to report, connect this with the reverse mathematics, with the level 1, level 2, level 3. So you'll see lots of similarities. Okay. So the first order strengths. So what I'm going to do is I'm going to talk about a special case of TT1, which is color a single node. And then I'll mention something like TT22. So that's more or less we have been doing. Okay, so let TT1 denote the following statement. For every K, TT1K. So if you color the binary tree with every single node, you color it with one of the K colors, then there is a homogeneous tree, isomorphic to the original tree. Okay. Now with suppose you do this on standard models, so or with I sigma 2, then this problem always have computable solution, always have recursive solution. So just use density argument. So it's very easy to find a solution, and it is recursive. So the problem become more interesting if you don't have this sigma 2 induction. So it is known that TT1 will imply B sigma 2. Oh, I forgot to mention. So TT1 certainly is a generalization of RT1, which is pigeonhole principle, the pigeonhole principle. So therefore, TT1 definitely imply B sigma 2 because pigeonhole principle would imply B sigma 2. Okay. So, but several other people, Condon, Grossek, and Miletti, they showed the TT1 is actually strictly stronger than B sigma 2. So they asked the question, does TT1 implies I sigma 2? right? So it's similar to the RT for the pigeonhole principle. So from Hurst result, we know it is it is higher than second level. The question is whether it implies a third level, right? So we want to find the exact location. Okay. Now, it turns out between the first level, this is first level of the first order measurement, B sigma 2 is a second level, and then I sigma 2 is a third level. So it turns out there's another axiom called P sigma 1. It is also between first level and second level, and it is independent with B sigma 2. So it is known that if you add them up, it is still below I sigma 2. So I don't have time to explain what exactly it is. So it is known that B sigma 2 is incomparable with this P sigma 1, and together they do not imply sigma 2. So with my colleagues, Chita, Li Wei, Wang Wei, and me, so we are able to show that TT1 is pi 1 conservative over RCA0 plus B sigma 2 together with this P sigma 1. Consequently, TT1 is strictly weaker than I sigma 2. So it is between the second level and the third level. Okay. And recently, we just submitted a paper similar to Partey and Yokoyama's result. We are able to show that TT1 is pi 0.3 conservative over RCA0. So consequently, TT1 does not prove this P sigma 1. So it's a very similar. So this is a parallel result. Actually, we used their techniques, but there are extra difficulties, of course. So here's some questions. So the TT1 and RT22, in some sense, they are similar. So, but we don't know their relation. So the one open question is, over RCA0, does RT22 imply TT1? So we have no idea. The other way is TT1 does not imply RT22 is because over standard models, TT1 have very simple solutions, have a recursive solution, and RT22 has complicated solutions. So so we know TT1 does not imply RT22, but we don't know RT22 whether RT22 implies TT1. Okay. Okay, let me skip this for. There are a few slides. Let me skip. I'll jump to TT22. So the slides I skip is there's another famous combinatorial theorem talking about coloring on product of trees. But I'm afraid I don't have time. So let me finish the main talk first. So just now I finished talking about TT1. So now I want to look at coloring the pairs, right? TT1 color a single node. So what happens if we color a pair of nodes on trees? And I will make comparisons with RT22. You'll see again, they are very, very similar. Okay, so clearly that a tree version is more complicated than the, I call it line version, right? On the straight line, the natural number line. So therefore, on the other hand, ACA0, you can show that ACA0 implies TTNK. So therefore, borrowing Jacob's result, because if for n is bigger than 3, RT 3, 2 already equivalent to AC0. So therefore, the TT NK is also equivalent to AC0. So in other words, they for the big brothers of Ramsey theorem for trees, we can also characterize them as they are exactly at the third level, okay, AC0. And Jafarov and Partey showed again the younger brother is the most interesting one. So if you color the pair of node, and then this is strictly weaker than the rest, right? So the TTNK is equivalent to AC0, but this TT2K is really weaker. It does not imply others, okay? And they also try to mimic the divide and conquer method. So they can decompose the TT22 into two versions, a stable TT22 and a cohesive TT22 and so on and so forth. So this is, again, very similar to the decomposition done by Cholak, Jakosh, and Slayman. Okay. And recently, with Chita, Live, and Liu Lu, we showed that TT22 does not imply WKL0. So this is parallel to Liu Lu's result for RT22. Remember that I draw this picture before. So this is level 3. AC0 is level 3. WKL is level 2. RCA0 is level 1. Just now I was saying RT22 is here. Okay, is to the side. Okay, to the side of WKL0. Now TT22 is it's the same. So TT22 is also to the side. Okay. And an ongoing project with the same group of people, we are trying to pinpoint the first order strengths. So we want to say that TT22, we want to show that TT2 does not imply I sigma 2. And to do that, we probably need to show that every recursive problem or recursive instance has a low 2 solution. But this is still going on. So, okay. Now, I want to finish this talk by some kind of philosophical question, right? So, so look at the zoo below AC0. Just now, there's a very chaotic zoo over there. So we are trying to, so people study reverse mathematics. We are trying to measure the relative strengths of mathematical theorems. Now, it's quite likely that the strengths are not linearly ordered. But if it's like a zoo, it's not very satisfactory, right? So if everything turns out to be chaos, no order at all, then it's to me, it's not nice, right? So now we know there are theorems which give you a partial order. But on the one hand, we know there are natural examples which give us a partial order. On the other hand, I don't want partial order to be so chaotic. So is there a balance? So is there a nice way to, are there other principles which guide us to find a good, how to say, landmarks or milestones so that we can characterize the typical mathematical theorems, right? So look at the zoo. So which other principles are more important in the sense of reverse mathematics, right? So there are lots of animals, but I don't believe all animals are created equal, right? Some animals are more interesting than others. So we suspect that this Ramsey theorem or Ramsey type theorems is a candidate because it is an important combinatorial theorem and it has lots of applications. So, but if you look at the zoo Ramsey theorem, unlike the big five, it doesn't attract lots of, it doesn't have lots of equivalent theorem. How to say? Although it has lots of consequences, but it seems there's no natural theorems in analysis or in algebra which is equivalent to RT22, right? So even for the Ramsey theorem for trees, Partey showed that RT22, for example, is strictly weaker than TT22. So even TT22, which looks quite similar to RT22, and they share lots of similarities. In the previous two slides, there are all similarities between TT22 and RT22. But however, strictly speaking, the strength of TT22 is strictly bigger than RT22. So that brings me the question. So we are trying to find, so maybe we should tolerate some how to say. So although TT22 is strictly is not equivalent, okay, not equivalent to RT22, but there are lots of similarities. So maybe we can somehow characterize these similarities. So we can find a family of Ramsey-like theorems, and although they, strictly speaking, they are not equivalent, but they are so similar, you can put them in the same place in the zoo. So I was wondering whether the family of RT22, TT22, Millikan, or Radograph, all these things, the Ramsey type theorems, maybe we can find some other measurement or other criterions so that we can characterize them in the same group. So I guess I'll stop here. I have to leave a little bit early because I have to teach at 7. So that's why I'm in a rush. Okay, I'll stop here. Thank you very much.
Thank you, Prof. Yang. Maybe we can have 1 or 2 questions. Any question?
Let me stop sharing.
Okay. Any question?
I guess I'll ask a question. This is it's a stupid question, I guess. So Yang, you mentioned at the beginning that one of the motivations for developing the reverse mathematics is to find new proofs for different theorems. Of course, over here, of course, my understanding is that not only you find new proofs for some of these implications, but also you find sometimes there are no proofs, right, from one thing to another. Do you feel that these new proofs that we found have played some role, like for example, in discovering new mathematics or new facts, or do they eventually lead to maybe there are some examples where some of these reverse mathematical results will lead to changes, sort of new understanding in the subject that we're studying.
Yeah, so that will be our dream. Or so so for example, the theorem of TT22, we would think this is a very natural theorem. Maybe combinatorists have studied this before. But it turns out, is at least from the literature I know, that there's no clear formulation for TT22. There's TT1 maybe, but TT22. So I know that the TT2 is not such a big important theorem so far, or it's but somehow in the study of reverse mathematics, we from time to time we did formulate some new theorems, but we certainly hope that we will discover some new theorems which have impact. But I'm sure there are examples, but very few. Yeah, sorry. It's okay. Can I make a side remark? So once I gave a talk in Chinese Institute of Systems, 系统所. So there are people study mechanical or machine-aided proofs. So again, they are very sympathetic to reverse mathematics. They say they also face the same question. People ask them, okay, you analyze other people's proof, right? Try to make it, you can prove it by machine. Now, do you prove new theorems? Well, they'll say that, okay, of course they are trying to prove new theorems, but at this moment, even to catch a big part of the available theorems is still difficult for them. So yeah, so hopefully eventually, when the techniques are developed or the field is more matured, and then we can push the boundary of mathematics. Okay. Yeah.
Okay. So I think we will thank Professor Yang. Although there is another question, maybe you can DC, you can email the Prof Yang about your question. We can let the Prof Yang go and go to his class. Thank you very much once again, Prof Yang, for the very interesting talk. I hope everyone benefits. So
okay, thank you, Zuyang. Okay.
Thank you. Okay, so we're going to take. Thank you. We're going to take a break for 2 hours, and then we will meet again after 2 hours. That would be 9 o'clock in Malaysia and Beijing and Singapore. And then that will be 1 o'clock UTC. And I think that's 2 o'clock in the UK. Okay, so there will be a 2 hours break, and then I'll see everyone again later. Thank you.